why don't you give a course about how smoothing equations can be useful for Pólya urns? So this is what I'm going to try to do, but I'm putting it between brackets because this is really only going to be maybe the second hour of the course. So I have 3 hours. The first hour is going to be more an introduction to Pólya urns. The second hour is really going to be about smoothing equations, and we're going to be how they can be useful for Pólya urns. And in the third hour, it depends how fast I go, but I might have to do something completely different with multi-drawing Pólya urns, so something a bit more recent. And I think it's interesting to see, you know, what's the current research for Pólya urns is at the moment. Okay, so but first, you know, what is a Pólya urn? So lots of you in this room are specialists of continuous time branching processes like multi-type Galton-Watson processes, and actually this is the discrete version of multi-type Galton-Watson processes. So to me, somehow the multi-type Galton-Watson processes are the embedding in continuous time of Pólya urns, and maybe to you, Pólya urns are going to be the discrete time version of multi-type Galton-Watson processes. So what is a Pólya urn? It's an urn in which you have balls of different colors. So in this talk, I'm going to have only 2 colors in my urn most of the time. So let's say, in this example, blue balls and red balls. And I choose, at the beginning of my little experiment, I choose what I call a replacement rule. So let's say, you know, something like this. And red gives, you know, blue, blue, red, red. Okay. So then what happens, at every time step, I'm going to pick a ball uniformly at random in the urn. Okay, so let's say I picked this one. Okay. And then I look at its color, it's red, which means I'm going to apply this replacement rule. And this replacement rule, by convention, means I put back this ball into the urn, so I leave it there, and I add 2 blue balls and 2 red balls in my urn. So here, okay, 2 blue balls and 2 red balls. And then the idea is that I'm going to do that so on and so forth, right? And the question we ask is, what is the composition of my urn? Okay, what is the distribution of the colors when time is large? Okay, so it sounds very easy, but it's not. Not always, not always. Okay, so of course I'm not going to draw these nice replacement rules as pictures in the following. So I'm going to introduce the replacement matrix R, which is a way of encoding this rule. So here it's 3, 1, 2, 2. I hope you understand why, right? It just tells me if I have a blue ball, then I add 3 blue balls and 1 red ball. If I have a red ball, then I add 2 blue balls and 2 red balls. Okay, so what is the object of interest? It's just this composition vector u of n. So it's u1 of n, u2 of n. And this is the number of blue balls in the urn at time n, and this is the number of red balls in the urn at time n, okay? So this process is entirely defined by 2 parameters, which are the initial composition vector, okay, which tells me what is in the urn at time 0, and R, the replacement matrix. And also, from the definition, you can see that this U of n is a Markov process, right? Okay. So, of course, as I said before, the main question in this talk is going to be to be able to describe, you know, U of n equals what when n is large. And of course, you can expect, and one interesting question is, you can expect it's going to depend on the initial composition and the replacement matrix, but does it really depend on both all the time somehow? So we're going to see examples where it does depend on both, and examples in which it does depend on the replacement matrix, but it doesn't depend on the initial composition anymore. So you forget the beginning. Okay, is the model clear? Because if not, you're going to be in trouble. Good. Okay, so let's start with the first Pólya urn that was introduced. I think it was introduced, I mean, at least it dates back to Pólya and Eggenberger in the 1920s. So I call it the original Pólya urn. And so this is Pólya and Eggenberger. Pólya and (1920s). Okay, so actually, so this is the only section. Actually, this was, okay, in my notes, this is 1.2 and 1 was the introduction. Sorry, I'm going to try to keep a precise precise plan of the talk. Okay. So this is the only section in which I'm going to allow myself to have more than 2 colors, right? So it's quite natural. You could imagine that you have more than 2 colors, in which case your replacement matrix is, say, D times D, and you have a D-dimensional composition vector. So this is what I'm doing just for this example. So take D colors, and I'm doing it because it's going to be useful in the following. And take U of 0 being something, so I'm just giving it a name, so alpha 1 up to alpha D, these are just integers, and take R equals some big S, which is also an integer, times the identity. So this matrix is just, you know, S, S, and 0 is everywhere else. So what do? I pick a ball uniformly at random in my urn, and if it's of color I add S additional balls of the same color in the urn. So this was really the first Pólya urn studied, I think, or at least with S equals 1, right? But we're going to do it directly with S larger, because it's not much harder. And I think it was introduced originally as an epidemics process, like they wanted to model the spread of epidemics. So nowadays it seems a little bit simple, but this was the original motivation. Okay, so what can you prove about this Pólya urn? Let's state the theorem. So this theorem dates back to Pólya and Eggenberger for S equals 1, and later it's been studied by Blackwell and Kendall in '64, and also later Athreya, Johnston, and Scott, etc., all in more and more general versions. So what you can prove is that almost surely, when n goes to infinity, so at large time, and also in all LPs with p larger or equal to 1, we have that u of n divided by n times s. So this is not very surprising, right? So at every time step, I added s balls in my urn. So if I want to have a chance to converge, I need to divide by n times s, right? Because the total number of balls behave like n times s. This goes so almost surely and in all LPs, to some random variable that I'm going to call v, and this v is distributed as Dirichlet alpha 1 over s, alpha d over s. Okay, so maybe you don't know what the Dirichlet distribution is. I'm going to tell you a little bit about it in a minute, but I already want to comment on this result. So I want to comment because this limit here depends on the initial composition of the urn. So I didn't forget the alpha i's were the number of balls of different colors in the urn at time 0, and they appear in the limit. So they are not forgotten somehow. Okay, so what is the Dirichlet distribution? Can I have this pen? Okay. So the Dirichlet distribution. Maybe everyone knows it already? Okay, who knows the Dirichlet distribution? Okay, so I'm going to define it. Great. Okay, so the idea is that it's defined on the simplex. So the simplex is called sigma, and it's the elements x1, xd in 0, 1 to the d, such that the sum of the xi's is 1. And so a random variable v takes values on sigma, and the density of, say, v, this v, on sigma is given by, so let me write it there maybe, is given by gamma nu1 plus nu d. This is when I really need my notes, divided by gamma of nu1 times gamma of nu d times the product of g equals 1 to d of xj nu j minus 1. And then you just take the Lebesgue measure. I don't know how to write this. Yeah. Yes, so if you do the Kingman coalescent and then you take a sample of what you get, it's the Ewen sampling formula stuff, right? Oh, it's a Poisson Dirichlet. Is it Poisson Dirichlet for the?
I thought it was Dirichlet. The one with the mutation? No, just Kingman, so coming down, when Kingman comes down to n, to n into n blocks, I think the math function is.
Yeah.
Is it Dirichlet with uniform? Yeah, with all the alpha.
With ones.
Are they alpha?
Yeah, alpha. With 1 over something maybe, or all ones?
Yeah.
1, 1, 1, 1, 1. Yeah, so when it's 1, 1, 1, 1, 1, then it's actually the uniform distribution on the simplex, if I'm not mistaken. This was one remark. So this is just the Lebesgue measure on sigma. So yes?
The Dirichlet appears in the multi-type right-Fisher diffusion.
So at this point, I thought I would make a remark to say that yes, this, if you integrate it on sigma, it gives you 1. So you can do it as an exercise. I'm not sure it's very interesting. I have a better exercise, which is not maybe, it's a calculation exercise, but I think sometimes it's good to practice calculations. So if you think so, to do it. If really you don't like calculations, don't do it. So we can calculate the moments of this Dirichlet distribution.
No, actually, it's a good exercise.
Okay.
And it's useful for my exercise as well.
Yeah, I think it's useful. I mean, you can, yeah. But it's calculations, right? But okay, so take taking Dirichlet something, nu1 to nu d. Okay, and show that the expectation of d to the p, so this is just a notation to say expectation of d1 to the p1, d, lots of d's to the p d. So you can show that this is gamma of nu. I'm going to define what nu is. Gamma of nu plus p, product from 1 to d of gamma of nu j plus pj. Again, it's going to be useful later, otherwise I wouldn't be writing that. Gamma of nu j. Where mu is the sum of the nu j's and p is the sum of the pj's. Yeah, I think it's quite a tricky exercise, but it's fun. I mean. Cool. Okay, so now we are ready to, so is it okay, the Dirichlet distribution? Nice. So now I'm just going to give you a sketch of the proof of this theorem, because it's quite nice. I'm going to skip the technical details, and I don't suggest them as an exercise because I do think they are not super interesting, but if you want to do them, please do. So proof of this theorem. So let alpha be the total number of balls you had in the urn at time 0. Just a notation I need. Then we're going to show that there is a martingale in all that. So I'm going to un multiplied by some nice function of n is going to be a martingale, and to find the nice function of n, I just calculate the conditional expectation of un plus 1, knowing everything that happened until time n. Okay, so what's that? Well, so first I've only added things in the urn, so I keep what I had in the urn at time n, and I might add something new. So what do I add? Well, for each color, with probability, the proportion of balls of this color, okay, which is uj of n over the total number of balls. So the total number of balls is the number I had at the beginning plus s times n, because at every time step I add s balls in my urn. So with this probability, I've used the jth line of the replacement matrix, okay? Which means that I've added into my urn rj. Rj is the jth line, but now I put it vertically, okay? Does it make sense? Rj, so let's do an example. R2 now is like 2, 2. So it's the second line, but put vertically, because my un is vertical. Okay. But this time, Rj is a bit easier, right? Because we know that this is S times Ej, where Ej is the jth vector of my basis. All good? Good. Very nice. So if I rewrite this properly, uj times n times ej, if I sum, let me do a step. U of n plus, I put everything that doesn't depend on j outside. Of uj of n, ej. But this, since this is my basis, this is just u of n. Right? So somehow what I've written now is that this is alpha. I'm a bit lost suddenly. No. What do I have at the top? I have alpha u of n coming from here plus s. I'm lost. I'm really lost. S n u of n coming from here plus s u of n coming from here divided by alpha plus s n. So this was very pedestrian because I was getting confused, but it's basically alpha plus s times n plus 1 over alpha plus s n u of n. So somehow now I have almost a martingale. I just need to renormalize by this thing so that it gives me a martingale. Okay. So let me write it for you. Come on. Okay. So while I was doing the boards, you had time to find the martingale. And you're going to have some extra time. Come on. Here. Okay. So we have proved that u of n divided by alpha plus ns is a martingale. Okay, good. And it takes values, taking values in 0, 1, d. Okay, so actually each of the projections on 1 to d are also martingales. They are also non-negative, so all of the coordinates converge almost surely to something. So somehow you know that this thing converges almost surely to something that I call v, right? So you use that each of the coordinates is a non-negative martingale. Good. Okay, so now I want to skip the rest because I started doing it on my note and it wasn't super interesting. So I thought I don't want to bore you to death. But basically, the idea is to use the moments. So you calculate the limiting moments of this thing, and you find that they are equal to the moments of a Dirichlet distribution. And then you say a Dirichlet distribution is characterized by its moments, therefore the limit has to be a Dirichlet. Again, if you're bored this afternoon, please go ahead. I have half of it on my notes if you need help to start with. Okay.
May I ask?
Yes, please.
So it seems from the proof that if you make alpha, so here the alpha disappears because it's less than n times s.
Yeah.
And so if I would take alpha depending on n, but still less than s of n, it looks like I still have a martingale. This I want. It's still true that I have a martingale, but maybe it changes the limit law or.
It could change, right? Because in the limit you also have the alphas, right?
Yes.
So
maybe we have convergence, but
to something different. Yeah, I never asked myself that, so I don't know. But yeah, good question. You're asking because you do that in your model.
Yes.
Yes, please.
Say b equals 2, alpha 1 equals alpha 2 equals 1, and s equals 1.
Yes.
It seems to me that they should be like, this limit should be 1/2 and 1/2, no?
Well, it is on average, indeed.
On the ends of your segment, no?
No. So that's not all. So it is a random variable between the two, but it depends on it's random. Yes. So the simple example that maybe you've done as an exercise when you were younger is the 1, 1, 0, 0. And here, as a limit for the first color, you find a beta distribution, so it is random. So on average, it's indeed a half, but it is random. So yeah, it's a very good question because actually I wanted to insist on the fact that the limit is random. So it's not deterministic. It's not like a strong law of large numbers. You don't go to a constant. You go to a random variable. Okay, so let's do something a bit more complicated now because this diagonal was too easy. It wasn't so easy, but anyway. A different case. Oh shit, and I messed up again. Okay. A different case when R is irreducible. So R, maybe just to fix ideas, right? So R is irreducible if and only if for all ij there exists n such that if you put the matrix to the power n, then Aij is positive. In terms of the urn, it means that if you start with one ball of any color, say of color 1, but you could do it for any of the other colors, at some point in your realization, you're going to see balls of any colors. Okay, so if I fix I and j and I start with one ball of color I, I'm sure that at some point in history, I'm going to see a ball of color j. So you have some kind of mixing somehow happening, right? So, and of course, it's very different from this case, which was diagonals, not at all irreducible, right? So it's going to be very different. So let's do it for 2 colors, right? Because I told you most of this course is for 2 colors. So let's go back to 2 colors. Here, irreducible means that it's not triangular. So neither B nor C, I forgot my replacement matrix. So R was A, B, C, D. Neither B nor C are equal to 0. Okay. So we know that by the Perron and Frobenius theory, we know that the 2 eigenvalues of this matrix are going to be real. Okay. And actually, I'm going to do one additional assumption. I'm going to assume that the urn is balanced. So what does that mean? It means that A plus B is always equals to C plus D. And I call this number big F. Okay, so this was the case in the first example I gave, because I was always, if I forget the colors, I was always adding 4 balls in total. So here I'm just saying I want to control exactly how many balls I have in the urn at time n, and I'm going to have the initial number plus n times s. And it helps me for the study. It's not quite necessary, but just for the course, please, let's do that. So if we do that, you can check that S is the largest eigenvalue of R. S is the largest eigenvalue of R. And you can calculate the second one. So let M be the second one. So I did it for you. This is really not good. Here. So if you know multi-type branching processes, really, you're in familiar territory, right? Because you know that the asymptotic behavior depends on the eigenvalues of your replacement matrix. And so here, somehow, it's the same, which is no surprise. OK. La, la, la. OK, so this is the second eigenvalue, and actually, you can calculate it. Did I write it on my notes? I didn't even write it, so let's not. You can calculate it if you want. I didn't. Sorry? It's A plus A plus what? T? B. D. Yeah. Ah, that's very clever. Minus S. Well, yeah, thank you. Thanks, Min Min. Cool. And you can also calculate the eigenvectors. You don't actually need to calculate them, but you know we have formulas, so well, maybe I shouldn't calculate them then. V1 and V2. This is associated to S. This is associated to M. And you also have the left eigen, how do you call them? The eigen functions? Eigen what function? The linear values, the dual basis? Dual basis, which is u1 of xy is equal to x plus y over s, and u2 of xy is equal to bx minus cy over s. Okay, so the dual basis of V1 and V2. Okay, so we've done all our little eigenvalue analysis, and the big theorem, which dates back to Athrea and Karlin in 68 approximately, tells you that almost surely when n goes to infinity, then u of n divided by n, so again, no real surprise, right? I need to divide by n because my mass increase linearly in n goes to V1. Okay, so let me comment, because I think this result is really, really nice. And we're going to compare it to the result we had before, so the result for when the matrix was diagonal, the Pólya and Eggenberger result. So two remarks are, I think, important. The first remark is that the limit is deterministic. Whereas before, you asked me, oh, isn't it weird? This limit is random. V was random. Here, this is completely deterministic, right? It's just the eigenvector of R. So 1, the limit is deterministic. And 2, this is the eigenvector of the replacement matrix. So I have completely forgotten where I started from. So the result doesn't depend on the initial composition. It doesn't depend on u of 0. So if you want, I usually say that this is a strong law of large numbers for Pólya urns, right? So in that case, we really have almost sure convergence to something deterministic, and that doesn't depend on where I started from. So that's very, very different from what we had in the diagonal case. So I'm not going to do the proof, because this is basically embedding in continuous time, and you get a multi-type Galton-Watson process. And I'm going to tell you continuous time. I'm going to show you this embedding in continuous time anyway, so good. You can also prove it directly in discrete time, but the martingale, so you can do exactly what we did up there. You can exhibit a martingale, but it's not an easy martingale, and the proof is you can do it, but it's not very nice, whereas if you embed in continuous time, you do the multi-type Galton-Watson processes, and in 2 lines you're done, right? I mean, I'm exaggerating, but a little bit. 2 lines? Okay, so let me show you this embedding in continuous time, and what do I mean by that? Okay. So to embed in continuous time, I'm just going to imagine that instead of having this discrete time, and at every discrete time step, I pick a ball in my urn and I do the replacement thing, I'm going to just let the balls split at random times on their own. Okay? So this is section 2, embedding and I'm going to show you that this object is more or less the same as a multi-type Galton-Watson process. So you already know that, so you can have a little nap. Okay, so the idea of this process is that I'm going to start with, in my urn, I'm going to have alpha red balls and beta black balls. Okay, and then time is continuous now, so this is going to be a very fancy drawing here. I'm going to equip each of these balls with a little clock. And this clock follows an exponential 1 distribution, and they're all independent of each other. So each particle is equipped with an exponential 1 clock. They are all independent, okay, I'm not writing it. All the clocks are independent of each other. When a clock rings, the ball associated to the clock splits into, and this is where, of course, it depends. So it splits into A plus 1. So I'm going to explain the plus 1, but red balls, if it was red, and B, and B black balls, if it was red, and C red balls, and D plus 1 black balls, if it was blue. Oh, blue and black, yeah, okay, sorry, black. And I think I exchanged the colors compared to the example, but, you know, relabel the colors. Okay, so why the plus 1? It's because, you know, when you do a multi-type Galton-Watson process, you want the particle that splits to die. And in my urn, it didn't die. I was always leaving it there in the urn. So somehow it's the same with exponential clocks, to die and be reborn than to just stay alive. So that's why I die, but I'm reborn. So this is the reborn particle that just splits. Okay. Anyway, it's an exercise to convince yourself that if I take this process, so let's call this process so U Ct for continuous time at time t is the content of the urn at time t. Okay, so the vector, the composition vector at time t. Exercise. So I'm going to say it out loud here. You're going to need to use properties of these exponential clocks, right? So I chose exponential clocks because the exponential distribution is very nice. It's very nice for 2 reasons. First reason, it has no memory. Cool. And second reason, if you take the maximum of, say, 2 exponential, the minimum, I wrote maximum, it's very confusing. The minimum of 2 exponential of parameter 1, then this is distributed as an exponential of parameter 2. So you're going to use this, and if you get stuck because you don't know very well these properties of the exponential, just come and see me and I can give you a list and we can prove it together. But basically use this to prove that if tau n is the time of the nth split, then if I take my urn in discrete time, so let me write dt, it's the one I defined before, at time n, as a process, it's equal in distribution to the continuous time taken at time tau n as a process. So basically, you imagine you have this process where, you know, you do nothing, you just have this thing splitting and splitting, and every time you hear some clock ringing, you take a picture, and then you just look at this picture, saying picture 1 is time 1, time 2, etc. What you see is just a discrete time process. So they are basically the same. But of course, they are the same, but if they are the same, you know, why bother? Okay, why bother? Because in continuous time, I have independence. So each of the balls, you know, it's like the branching property, right? Each of the balls is going to behave completely independently, right? Its descendants is going to behave completely independently. Whereas in discrete time, to know what's the probability to pick up this ball here, I needed to know how many balls I had in the urn at time n. And somehow this total number was creating dependencies between the colors. Whereas here, I can just isolate this ball here and ignore all the rest. And this, you know, just gives me a Pólya urn completely independent from the rest. And this is the branching property. OK, so it's good to put in continuous time, but these toe ends here, they are random. And if I don't understand them, it's going to be hard to take back the results in discrete time. So one thing we need to do before today is to try to understand a bit better how these toe ends behave. So let's do that. And coming up is my favorite trick in the whole probability theory. So I think your expectations are going to be here. But so let's see. So 2.2, asymptotics, totics of toe n. OK, so let's denote, let n of t be the total number of balls in the urn, the continuous time urn, right, at time t. OK, so actually, n of t, we talked a lot about Yule processes. N of t is a Yule process, right? Because, well, you can convince yourself. But anyways, my favorite trick in the whole probability theory is the following. So the lemma, it's not too hard, right? But the lemma is that exponential minus t times nt goes to an exponential 1. You all know that, right? So you're like, OK, almost surely. And the proof goes as follows. So it's easy to prove that this is a martingale. E to the minus t n of t is a martingale. This is an exercise. Should be the easiest exercise so far. It is also non-negative, right? Because this is non-negative and this is non-negative, so it converges almost surely to something that I'll call xi. And now the question is, how do you prove that xi is exponential 1? And I'm very pleased that we have Mariana's course, because you have two methods to do that. You have my favorite method that I'm going to show you, but you could also do a smoothing equation. So as an exercise, you're going to prove, using the branching properties of n, using branching, prove that xi satisfies a smoothing equation. And then you go to Mariana, and hopefully by the end of the course, we're going to be able to prove that the solution to the smoothing equation is the exponential 1. And I think it's actually unique if the mean is fixed or something. Well, we can study the smoothing equation later. But I don't want to do that. It's one of the ones yesterday. Yeah, it's, well, but I don't want to say which one it is. But yeah, it's a very simple one, and I think we had it yesterday. And it's a sum, it's not a maximum. Cool, but now let's do my favorite proof of the fact that this is exponential 1. So if we look at these toes, we know that the first ball, so we're going to start. Oh. Okay. Okay, so we start with one particle. I'm just going to calculate the probability that tau n is less than, and let me use the same notations as in my, oh, sorry. So I want to calculate the limiting distribution of n of t, basically. So I'm going to calculate the probability that n of t is larger than x. This is the same as saying that the time tau x has happened already. So tau x is less than t, right? So I've already had at least x splittings. I think I'm a bit confused. I'm so sorry. I forgot the s in all that, right? We all agree I forgot the s. Sorry. And so this is maybe not a gamma, an exponential. Let me see. Okay, sorry. Yeah, there is. I always get confused with this s, but it should be correct in my notes because I know it's not correct in my notes. Let's do s equals 1. It's a bit cheating, but yeah. We're going to see it in the proof. So as an exercise for tomorrow, I can do the s equals s. Let's do s equals 1. So you really have a nice Joule process. You always add only one particle. It's all very nice. So we want this. It's maybe in my notes, it's -1 here. Yeah, because at the one split, I have 2 particles. You have a little gap here. This tau x1, what happens? Basically, the first split happens at time tau 1. Okay? And then you have 2 particles alive. Each of them splits at time exponential 1. So we know that the second split here, this interval, is going to be an exponential 2. So this was exponential 1 because I had 1 particle and I waited for it to split. This is now exponential 2 until the next split because I have 2 exponentials and I wait for the first one to split. So I'm using here that the minimum of 2 exponentials is an exponential of the sum of the parameters. Then here I have 3 particles. So the next time is exponential 3. And all these times are independent. Okay? So what I'm saying is that tau x -1 is just an exponential 1 plus an exponential 2 plus blah, 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 plus an exponential, and this is where I usually get confused, x -1 is less than t. And these exponentials are independent. Okay, but now you're like, okay, great, am I going to have to do a huge integral or something? No. This is where I have a great trick. I'm going to do a drawing. Usually no one understands it, so don't worry. So I'm going to draw. So I'm going to start drawing x -1 exponentials. And I write their value as the height of the little stick. So exponential 1 is small. I have, a little stick here. This doesn't really mean anything. It's just to do a drawing. The second one is big. It's like this. The third one is like this. The fourth one, like this, etc. And the last one is like this. So this is just, if this is height, the height here is my first exponential E1. This is my second exponential E2, E3, etc. Okay. Good. If I look at, okay, when did the smallest one, let's put this one smaller so that my drawing is not completely stupid. I'm going to look at the smallest one. So it's the minimum of x -1 exponentials. Let me put some green. This one here, this little interval is the minimum of E1 up to Ex -1. We know that this is distributed as an exponential of x -1. Okay. If now I wait for the second one, let's put it a bit bigger so that my drawing is not stupid. Now I wait for the second one. By the lack of memory of the exponential distribution, I know that I can completely forget what happened before. And what I have now running is x minus 2 exponentials, right? Because one of them is gone. Now I look what happens here. I have x minus 2 exponentials. Okay, I look at the first one, the minimum. This is minimum of E1, you know, tilde if you want, up to, you know, theta x minus 2. This is exponential x minus 2. And then I do that again. So you see me coming, I'm going to do that. And here I'm going to build up these little intervals. And at the end, what I get in total is the max of my exponentials E1 up to EX minus 1. So I've written that in distribution, the maximum of x minus 1 exponentials is equal to the sum of an exponential x minus 1 plus an exponential x minus 2 plus an exponential blah, 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 plus an exponential 1. So this is just the probability. Isn't that great? This is just the probability. Maybe you already knew that. I don't know. I find it great. So what we've just shown by picture is that this is the probability that the maximum of E1 up to EX minus 1 is less than T. And then, you know, these are independent exponentials. The maximum less than T means that they are all less than T, right? So it's the product, it's the probability that one exponential 1 is less than T to the x minus 1. And I want to skip some details. Oh, well, I skip them here as well. And you conclude. So, yeah, so I really got confused, but I think I remembered somewhere. Yeah. So I think I'm going to stop here because I need to, next time I need to write you the real result for n of t when s is not 1. And I'm going to make mistakes if I do it now. So there is going to be a gamma instead of the exponential 1, but I don't want to make mistakes. Yeah, so this trick works if you start with s ball and you add s balls every time, because then you just take exponential s. Yeah. But if you start with not s ball, then you have to do some branching argument to say it's as if I had started alpha Eules with s balls, and you sum exponentials, and this is why in the limit you have gamma. So okay, so what we can write, it's almost there. So what Andreas is saying is that if n of 0 is s, then we do exactly the same trick here, but we have exponential s, 2s, you know, blah, 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 and you get exponential 1 over s, I think, in there. Okay. Well, I can do it then. Okay. So let's do it. So you get psi equals exponential 1 over s. And so now what you say is that if n of 0 is, you know, I don't know, how did I call it? Alpha plus beta, you know, then you basically sum this alpha plus beta independent exponentials, and this gives you gamma of alpha plus beta. Because it's as if, right, if you start with alpha plus beta, each one is doing something independent, so they all go to an exponential 1 over s, and the sum of exponentials is just gamma. Thank you, Andreas, for saving me. Okay, great. So I think it is time, right? Or do I have? Let me think.
Does it change now to that top right hand?
Oh, good. Yeah, so now it's like, yeah, exactly. So let's change it. Thank you all.
Do you want me to chair the chair?
That's okay.
I feel insulted. I was totally that.
No, but I mean, maybe it's good. I can tell you.
E to the minus f t.
Yeah. Thank you. We did it. Okay, so next time I'm gonna write what we can get from this plus that, right? And it's gonna help us take information from discrete time to continuous time and from continuous time to discrete time. And then we're gonna study the asymptotic behavior.
I'm putting all these on the web page as well, so I'm kind of photographing everything.
Do you want me to smile?
I've just got your hand there.
It's just my hand, okay.
So,
Yeah,
you taking questions now?
yeah, sure.
So, I mean, this was now we open up writing.
So
That kind of really smells a bit of the total mass of the total mass martingale, the result of lemma.
the lemma.
Total mass martingale, the branching process.
Yeah, so basically, yes. So this tells you, this tells you how many balls you have in your urn. Yeah. Is that what you mean, or do you want? I guess you mean something.
So you said that we haven't seen the connection with dot Watts in detail yet.
No, not yet.
But can that result be rephrased? Your lemma, can that be rephrased?
Well, the lemma is just about the size of the population at time t in a Galton-Watson process, right? It is. I've shown you the Galton-Watson process, right? It's this one. So you have the replacement matrix,
Right.
which is A plus 1 B.
So that really is just the total mass.
Yeah.
Marking.
You know that by heart, yeah?
As a limit. And so it's nice that somehow it's an explicit limit.
Yeah,
Which is kind of what you said in your exercise.
yeah.
Take it as a, right, okay, you did say this, didn't you?
That,
You said just take the martingale of the
yeah.
Watson process, its limit exists, it solves the fixed point equation, and that gives you the gamma.
Yeah, exactly.
That's
So
another way to get the gamma.
that's another way exactly to get the psi.
So we've just answered another of Mariana's questions yesterday. She asked for
Really?
explicit solutions.
Oh yeah,
So you've now found that,
but it comes from branching.
yeah, but we only had exponentials yesterday. Now we
Yeah,
found
true.
gamma.
Time gamma. Yeah. So we'll see tomorrow what it's useful for. Other questions?
A comment, so just to let you know, I also think it's one of my favorite tricks.
It's
too.
also
And it appears in the length of the Kingman coalescent to prove a central limit theorem on it.
cool.
And maybe also in the height of the Boltzmann-Schneemann coalescent, this max of
Cool.
exponentials.
Yeah, you did mention it in your. No? Who mentioned it? Or Liz? No, okay.
If I update my talk, I was going to have the similar picture as well.
Oh, really? You like it too?
Update my talk. It's not there, it's because I've been lazy.
Well, you can do it again.
More questions? Thank you.
Thank you.